This is the fourth and last part of our discussion on the concept of limits of complex valued functions. So far, we have learned how to define the limits of complex valued functions, and we also observed and proved a very interesting relation between the limits of complex valued functions and the limits of real valued functions. And using this link, using this interesting and useful link, we are able to calculate limits of complex valued functions with much ease. Now, what is that link? Let's have a look at it again. So, if the complex valued function is given in this form, then calculating the limit of this complex valued function as z approaches to z0 is the same as calculating the following two real limits of real valued functions. Now, let's explore some further properties of limits of real valued functions. Of course, this will help us in calculating the limits of complex valued functions. So the first very simple observation is, if we are given the function to be 1, which is a constant, then the limiting value is also equal to the same value. So in fact, we can prove it by replacing 1 to be any constant c. Similarly, we can prove the following thing. When xy approaches to x0, y0, this function u of xy, which in this case is just x, should be equal to x0 and is equal to x0. So in fact, when I'm saying that it can be proved, it means that it satisfies the epsilon delta definition. For every epsilon, we should be able to find a delta such that the distance between x and x0 is less than epsilon whenever the distance between xy and x0, y0 is less than delta. So it must satisfy the epsilon delta definition. And similarly, we can show that this limit also exists and is equal to y0. And once again, by showing means it satisfies the epsilon delta definition. Now, there are some further properties of limits of real valued functions. So if there are two real valued functions, f of xy and g of xy, with the following limits. So if this limit as xy approaches to x0, y0 is a, and if this limit xy approaches to x0, y0 of g of xy is b, then we can prove that the limit xy approaches to x0, y0 of c f of xy is ca, where c is a real constant. Okay. And similarly, we can prove that as xy approaches to x0, y0, then the limit of this function f of xy plus g of xy is just the sum of their limits. Okay. And similarly, if we replace this plus with minus, then the same result holds. And if we are considering the product of these two real valued functions and calculating the limit as xy approaches to x0, y0, then it is equal to the product of their limits. And similarly, for the quotient, if we are taking quotient of f with g and calculating the limit as xy approaches to x0, y0, then it is equal to the quotient of the corresponding limits, in other words, a over b. And of course, to avoid division by 0, we impose the condition in this case that b should be not equal to 0. Now let's apply these results and prove this very simple limit. Okay, so we want to calculate the limit as xy approaches to 1, 2, and the function is 3x y square minus y. Now we can say that these are two different functions and there is a subtraction between them. Okay, so 3x y square minus this y. Okay, so if we say that this is the function f and this is the function g, then using this previous fact, this must be equal to limit xy approaches to 1, 2 of 3xy square minus limit xy approaches to 1, 2 of this function y. Now, once again, there is a product of two functions. So let's say this is first function x. Okay, so let's call it f and let's call it g. So once again, it is the limit of the product of two functions. So using once again previous result, we should be able to write it down in the following way. So this is equal to 3x. So let's say this is our first function f, which is 3x multiplied with limit xy approaches to 1 2 of function y square minus limit xy approaches to 1 2 of this function y. Now once again, this 3 is a constant, so that's why when xy approaches to 1 2, then the limit of x, we have observed that it is just x naught, and x naught in this case is 1. So this is equal to 3 into 1. And now this y square, it is in fact the product of two functions y and y. And in this case, once again, we can further write it down as limit xy approaches to 1 2 of y multiplied by limit xy approaches to 1 2 of y. And the limit of y, we have observed that it is just y naught, and y naught in this case is 2. So that's why it is equal to 2 multiplied by 2. And minus, once again, xy approaches to 1 2 of this function y is y naught, and y naught in this case is 2. So that's why it is just 2. Now simplifying this thing, we can easily see that this is equal to 10. That's how we implement the previous properties to calculate limits of real valued functions. Now let's use the bridge between the limits of complex valued functions and the limits of real valued functions to calculate this complex limit. Okay, so now in this case, our function f of z is z square plus z plus 1. And of course, if we want to use that bridge, then we want to write this complex valued function as u plus iota v. So let's first write down this function f of z in terms of u plus iota v. So z square plus z plus 1. So now f of x plus iota y is equal to x plus iota y square plus x plus iota y plus 1. So this becomes x square minus y square minus 2 iota xy plus x plus iota y plus 1. Now separating the real and imaginary parts, we get the following: x square minus y square plus x plus 1 plus iota minus 2xy plus y. Okay, so this is in fact u of xy, and this is in fact v of xy. Now calculating the limit as z approaches to iota is the same as calculating the limit this xy approaches to. So this iota is in fact 0 1. So we want to calculate this limit 0 1 x square minus y square plus x plus 1. Now using our previous observations and results about the limit of real valued functions, we can easily see that this is in fact equal to minus 1 plus 1, which is equal to 0, because the limit of this is the same as replacing x with x naught, which is 0 in this case, and the limit of this thing is the same as replacing y with y1, 1. So in this case it becomes minus 1, and once again this is 0 and this is 1, so this limit is 0. Now on the same lines, we can calculate the limit of v of xy. So limit xy approaches to 0 1 of this v of xy, which is minus 2 xy plus y. So this is equal to, so now once again x approaches to, x can be replaced with 0 and y will be replaced with 1. So that's why it is equal to 1. Now using these two limits and the connection between the limits of complex valued function and the limits of real valued function, we can easily say that this implies limit z approaches to iota of this function f of z is in fact equal to iota, because this is the limit of v, so there should be iota and it is 1. So the limit of u of xy is 0. Okay, so that's how we use these properties to calculate the limits of complex valued functions. Now let's define or describe some other properties of complex limits. So if we are given two complex valued functions f of z and g of z, And if these limiting values are a and b, then the first observation is the limit z approaches to z naught of c f of z is equal to c into the limit of f of z. And if we add these two complex valued functions and then calculate the limit, it is the same as adding the limits of these two complex valued functions, or we can replace this addition with subtraction as well. And similarly, if we multiply these two complex valued functions and then calculate the limit z approaches to z naught, it is the same as multiplying these two limiting values a and b. And on the same lines, if we are calculating the limit of the quotient of these two complex valued functions, then it is the same as taking the quotient of the limits, and of course in this case again b should not be equal to 0 because the division by 0 is not allowed. So these properties are very similar to the properties of the real valued functions that we observed and used earlier in this discussion. Now the proof of these properties are very simple. Now let's observe the first property and let's try to see how we prove this property. And of course the proof of the rest of the properties are very similar. Okay, so we want to prove that when z approaches to z naught of c of f of z, it is equal to ca, and of course what is given? So given in this case is limit z approaches to z naught of f of z is equal to a. And what do we want to prove? So to prove is limit z approaches to z naught of c f of z is equal to ca. So to prove this thing, once again we want to use the bridge between the limits of complex valued functions and the limits of real valued functions. So for that let's assume that this function f of z is given in the following form: u of x y plus iota v of x y, and the number, which is the constant complex number, is given as c naught plus iota c1. And let's first calculate what is c of f of z. So this implies that c of f of z is equal to u. Okay, so let's just write down u instead of u of xy, so it will simplify the calculations. Okay, so multiplied with c naught plus iota c1, so this is equal to u c naught plus iota u c1 plus iota v c naught minus c1 v, so which is equal to u c naught minus c1 v plus iota u c1 plus v c naught. So these are once again the real and complex parts of this function c into f of z. Now if f of z is equal to u of xy plus iota v of xy, and the limit a of this f of z as z approaches to z naught is u naught plus iota v naught, then using the connection between the complex limits and the real limits, we have the following connection. Okay, so xy approaches to x naught y naught of u of xy should be equal to u naught, and limit xy approaches to x naught y naught of this function v of xy should be equal to v naught. So why this is true? Because it is given that the limit of this function f of z as z approaches to z naught is equal to a, and since the real and imaginary parts are u of xy and v of xy, so that's why we have the following two limits which hold, using the connection of course between the complex and the real limits. So this limit is equal to u naught and this limit is equal to v naught. So this is given. Okay, so now if so we are also assuming that c is equal to c naught plus iota c1. So now let's see what is the form of ca. So ca becomes c naught plus iota c1 multiplied by u naught plus iota v naught. So this becomes C naught U naught minus C1 V naught plus iota C1 U naught plus V naught C1 C naught. Okay, so this is the number CA. Now we have also calculated, let's go back and see, we have also calculated the value of C into f of z. So this is equal to U C naught minus C1V plus iota U C1 plus V C naught. And if we calculate the limit of this function, limit z approaches to z naught, then it is equivalent to calculating the limits of these two real valued functions. And if I calculate the limit of this real valued function U C naught minus C1 V, then using this fact, now if our complex valued function f of z has the following real and imaginary parts, u of xy plus iota v of xy, and if the limit a is in fact u naught plus iota v naught, then using the connection between the limits of complex valued functions and the limits of real valued functions, we have the following two limits, that the limit xy approaches to x naught y naught should be equal to, of this function u of xy, should be equal to u naught. And this also implies that the limit xy approaches to x naught y naught of this function, of course real valued function, v of xy is equal to v naught. Now if we want to prove that the limit of z approaches to z naught of c f of z is equal to ca, then we should start from one side and prove that it is equal to other side. Now let's see what is this complex number ca. Now we assume that c is equal to c naught plus iota c1, and this number a, complex number a, is in fact u naught plus iota v naught. Now let's multiply them and find their real and imaginary parts. So c naught u naught minus c1 v naught plus iota c1 u naught plus v naught c naught. Now if we want to calculate this limit, then it is equivalent to calculating the limits of real and imaginary parts, and we have calculated the real and imaginary parts of this function c f of z. So the real part is u c naught minus c1 v, and the imaginary part is u c1 plus v c naught. Now let's calculate the limit of this real part, u c naught minus c1 v. Okay. So let's calculate this limit xy approaches to x naught y naught of u c naught minus v c1. Now we know that the limit xy approaches to x naught y naught of u of xy is u naught, and limit xy approaches to x naught y naught of v of xy is v naught. So using these two limits, we can easily calculate that this is equal to u naught c naught minus v naught c1. So here u naught c1 and c naught, so they are constants, and u and v are real valued functions. And using the properties of the limits of real valued functions, which we just discussed in this session, so we can easily calculate that this is equal to u naught c naught minus v naught c1. And similarly, on the same lines, we can calculate the limit of the imaginary part of the function c f of z. So limit xy approaches to x naught y naught of the imaginary part. So let's go back and see what is the imaginary part. So the imaginary part is u c1 plus v c naught. So this becomes u c1 plus v c naught. So using once again the same properties of limits of real valued functions, so this becomes u naught c1 plus v naught c naught. Now if these two limits hold, then this simply implies that the limit of z approaches to z naught c f of z is in fact equal to ca, because this number is in fact the real part of the number ca, and this number is in fact the imaginary part of this number CA. So if the real and imaginary parts are equal, so that's why this limit is equal to CA. Now similarly, we can prove the other properties of the limits of complex valued functions. Now let's use these properties to find the same example. Okay, so to calculate the same limit that we calculated earlier in this discussion, but earlier in this discussion we separated the real and imaginary parts and then we calculated this limit. Now let's use these properties which we just observed about the limits of complex valued functions, and let's use them to calculate this limit. Now this limit can be simplified in the following way. Okay, so this is equal to z square. Now z square is a multiplication of two functions, z and z. So we can write down this thing in the following form. So limit z approaches to iota of z and limit z approaches to iota of z plus, and of course the limit of the sum of the function is equal to sum of the limit of the function. So that's why we can also write down z approaches to iota of z plus limit z approaches to iota of 1. Now limit z approaches to iota of z, so it can be seen that this is just iota into iota plus 1. So this is in fact minus 1 plus iota plus 1. So cancelling out, the limit value is just iota. And observe that we have also calculated using other method this limit to be iota. Now this is the end of our discussion on the concept and calculation of limits of complex valued functions. Now this concept is going to be used further on in our discussion when we will see the continuity of complex valued functions. And of course, we will use this concept for the rest of our course as well.